Welcome back, everybody. Today we're going to be diving into Fourier series for the first time officially in the course, even though we've seen Fourier series pop up while doing separation of variables solutions the last 2 weeks of class. I haven't graded homework set 5 yet. I do have those to grade. I did grade your quizzes from Friday. You do have a quiz coming up this Friday at April 3rd. And then on April 5th, this Sunday, you have homework set 6. Homework set 6 deals with the transient and steady state problems. It also deals with eigenfunction expansions. So we've already gone over all the information that you'll need for homework set 6. Homework set 7, which is next Sunday, Easter, is the Fourier series stuff that we're talking about now. So just if you have any Easter plans or anything like that, just make sure that you're getting to that work sooner rather than later so that you don't leave it for Sunday next week to do. All right. Other than that, there's really no new announcements. It's sort of business as usual this week. We have our lecture notes, the eigenfunction expansion notes from Monday, and then we're going to be going over section 3.1 today. It's kind of a shorter lecture today because I really didn't want to jump into the stuff from 3.3 to 3.4 just yet. I wanted to do that as a group. So section 3.1 today is going to be a lot of Maple stuff. We're going to be dealing with a lot of Maple stuff involving Fourier series, talking about the different kinds of extensions that you can look at for Fourier series. So those notes will go up later today for you to look at. And then there's the 2 assignments that are due this week. All right, so let's take a look at it together. One of the things you're going to see that's going to be a little bit different is I'm going to do a side-by-side here. Eventually, I'm going to have once it's mirrored, eventually I'm going to have the lecture notes side by side. So hopefully these are big enough for everyone to see because I want to do it side by side with Maple. All right, drop that down just a little bit. Okay, so the big Maple file for you guys is the plotting Fourier series Maple file. It's number 14 listed there in Canvas. I'll jump back over to this here in just a second. But for now, let's go full screen with this. And what I'd like to do is talk about the classical Fourier series. So what we've discussed so far is that you can take any function f of x and represent the function f of x via this what we call the classical full Fourier series on the interval from minus L to L. If you're using sine nx and cosine nx, this is the interval from minus pi to pi. That's the classical Fourier series. The classical Fourier series is representing a function on minus pi to pi. That's what Fourier's original work was. But then that work was generalized given these orthogonal functions or orthogonal family of functions to the interval of minus L to L. So this is our what we call the full Fourier series. The Fourier coefficients, and these should be memorized. The Fourier coefficients are given by this, but we know from some of the things that we've talked about that this is really nothing more than the inner product of f of x with cosine n pi x over L. Excuse me. Over the inner product of cosine with itself. So we know where these formulas are coming from. This is that formula that we proved at the end of class. It was a little while ago, and we're going to do more with this in this chapter as well. Some of you were using a formula similar to this on the homework. But this is the definition of the full Fourier series. This definition should be committed to memory. You should know this front to back on exam 2. You'll have a chance to show me how well you know this definition. So sorry, this says March 30th. This is actually coming out on April 1st. And it's not April Fool's. You do have to know this. All right, so here's what I want to do, and turns out that I can pretty much get all the important points across with one example. I'm actually going to do two examples with you just to show you here, but I can get all the important stuff out of the way with one example. I want to compute the Fourier series of the function x on the interval from 0 to L, and then what I want to do is show you a bunch of stuff in Maple to graph it. Okay, so here's the idea. X is equal to, I'm just going to write down the Fourier series. It's a0 over 2 plus the sum, n goes from 1 to infinity, of an cosine n pi x over L. I'm looking at the interval from minus L to L. So L is 1. We're on the interval from 0 to 1. So if L is 1, then I'll just write 1 there. Plus bn sine n pi x over 1. So x is given to us by this series. In other words, a representation of the function x is given to us by this series if we have an infinite number of terms. However, we need the coefficients here. So the coefficients for an is 1 over L, which is 1 minus 1 to 1. The function x times cosine n pi x over 1 dx, or just this. And then the coefficients for the bn's are the integral from minus 1 to 1, so 1 over 1, x times, this will be sine. And this is good for 0, 1, 2, and so on, whereas this one is good only for 1, 2, and so on. Because if n is 0, you just get that term to 0 out. So if you wanted to start this at 0, the first term is just 0, which makes sense. And that's why we separate out the a0 term. Remember, the reason that we divide it by 2 is so that I could write this as one single formula. Because if I had to write a separate formula for the a0 term, it would be 2 over L instead of 1 over L. So that's the reason for having the a0 over 2 there. These can be put directly into Maple. Each of these formulas can, including this formula, to come up with the Fourier series. So here's the problem that we have, though. The Fourier series is only a representation of the function x on the interval minus L to L, which is minus 1 to 1. So I want to represent x on the interval from 0 to 1. So how do I extend it to minus 1 to 1? Well, we talked about extensions a little bit earlier in the course. The idea is we are left to choose how to extend the function x to the interval from minus 1 to 1, and there are 3 classical options. So the first option is you do what's called an even extension. We've talked about this before. The even extension of the function would look something like this. So you would have the function x defined on 0 to 1, and then you would extend it by reflecting it across the axis. So it turns out that this would be the actual function that is being represented by the Fourier series formulas up above. So if we chose to extend it evenly, then our Fourier series is going to approximate this function, not just the function x. Now, we could restrict the graph to 0 to 1 after the Fourier series is done doing its approximating, but this is technically the function that we're approximating. And remember the way that this works, the even extension of a function is f of x on, let's say, the interval from 0 to L, and it's f of negative x on the interval from minus L to 0. So this is the even function, which means that we'd be looking at the function x from 0 to 1, and we would be looking at negative x on the interval from minus 1 to 0. So this is what the even extension of this function would be. All right. The next example, or the next sort of classical extension, is what we call the odd extension. So the odd extension, we've talked about this one as well, at least briefly. So the odd extension would take the function x, the interval from 0 to 1, and it would extend it by flipping across this axis and then flipping across this axis. And if you do that, this is the picture that you will get. And so this is the function that you would be approximating all the way from minus 1 to 1 when calculating the Fourier series, full Fourier series above. So just remind you of the definition here. The odd extension of a function is that function defined on 0 to L, then 0 at 0, and negative f negative x for negative L less than or x less than 0. Now, here's the thing. On these, I'm including the endpoints L and minus L. That's actually not necessary. You don't have to include the endpoints. But we do need to talk about what's going on at 0. So I need to choose which function has 0. Here it doesn't matter because they match up. Here it doesn't matter also because they match up, but normally if they didn't match up on the odd extension, you're required to place 0 at the origin. All right, so that's the odd extension. One more extension here. Let me add a page real quick. And that is the shift extension. All right, so the shift extension, or the periodic extension, is the most interesting one. Because it's a little bit different than the others. The others are pretty straightforward. This one's a little bit less straightforward, but there are times when this one's more useful. And by more useful, I mean gives a better representation with less error than the other two. So we'd be looking at the interval once again from minus 1 to 1. And the way that this one works is, so you've got the function y equal x on the interval from 0 to 1. You simply just take it and copy it over to the left. So it's just a straight up copy over here. So this is 1 at that value. You just take whatever function is on the original window, so the window is the interval from 0 to 1, and you just copy it to minus 1 to 1. So the shift extension is defined as f of x on the interval from 0 to L. And here we have to be very careful with what goes on at 0, because these do not match at 0. So I'm going to include the original function at 0, but then this one will have an open circle. So how do you get the shift extension, by the way? Well, you're basically taking every point here and you're moving it to the left by 1. So this would be f of x plus 1 moves everything to the left by 1. And in general, it would be f of x plus L in this case. So f of x plus L is the shift extension here. And then this would be minus L less than or equal to x less than 0. So this would be the shift extension from this to this. And then you could periodically extend this window by saying that, f of x plus 2L is equal to f of Sx, right? So this is a 2L periodic extension, which basically means you're just going to take this picture here and copy it. So you've got minus 1 to 1, then from 1 to 3, you would have this exact same picture from 1 to 3. And then from 3 to 5, you'd have another copy of it. And we are going to do that with all of them, as you'll see here in a little bit. In other words, the periodic extension of the odd extension looks like this as well. So that's a 2L periodic extension. This is for L equal to 0, 1, 2, and so on. All right, and the even extension, same thing. So these are the three sort of canonical extension types. You can extend the function and calculate the Fourier series of this guy. You can calculate the Fourier series of this guy. You can calculate the Fourier series of this guy. So here's the big question that I want you to answer. And, don't cheat on me. Actually commit to an answer on this. Which of these three extensions do you think will give the least error? And what's your reason for that? So what we're going to do here in a second is take a look at Maple, and I'm gonna actually show you how to plot each of these in Maple so that we have the correct even extension, odd extension, shift extension showing up. And you're going to see which one is clearly the best, and there is a clear answer that's the best here. My question to you is, which one will that be? Now here's the other thing I want you to consider. We're going to be calculating this formula in Maple. And when we do that, we're going to end up calculating these integrals. Now these integrals are integrals on a symmetric interval. The function x that you're looking at on this interval actually isn't going to be x, it's going to be extended, it's going to be the extension function that we're actually calculating. Because you can't just do x on the interval from 0 to 1, because that's not how the Fourier series is defined. It's always defined on a symmetric interval. So, for instance, if I'm calculating this one, cosine is an even function. X, if extended this way, is an even function. But down here, sine is odd, and this would be even. So even times an odd is odd, and you're integrating on an odd interval. I suspect, and you should too, that the coefficients for the bn's are going to disappear if I calculate the full Fourier series on this guy. And similarly, the cosine coefficients are going to disappear here. And the reason is you're trying to approximate an even function. You only need even functions to do that with, and that's cosine. Sine is odd, cosine is even, sine is odd. We're going to talk more about that, but I want you to see it firsthand in Maple. All right. So bring this over here side by side. All right, that's about as good as I can do. Okay, so take a look at this together. We're going to start with the even extension. You can see what I did to create the even extension here. I defined the function f of x to be x on the interval from 0 to, make this a little bit bigger, defined it to be x on the interval from 0 to L. I then created the even extension by taking f of negative x. So basically I'm just recreating this formula, where I have named f of x to be the function on 0 to x. Now, you might be tempted to just say f of x equal x, but you can't do that because I'm only starting with the x on 0 to 1 here. So L is 1. I'm plotting the even extension function, and notice when I go to do the Fourier coefficients here, the an and the bn, I'm calculating the Fourier coefficients based on the even extension of the function, this function here. I've got the formula for the coefficients, and by the way, you should, if you're giving me an answer for this problem, here's what your answer should be. If you have the even extension and you're telling me what x's Fourier series is, you should say x is equal to, you can see here that a naught is 1, so this would be a naught over 2 plus the sum n goes from 1 to infinity of the an's. This is the formula for the an's right here. Remember, Maple doesn't know, like we know, that n is an integer, so you have to tell it, assuming that n is an integer, simplify that coefficient. So this is the coefficient formula for the an's. So that formula would be -2 plus 2 to the -1n over n squared pi squared times cosine n pi x over 1. And notice that the bn's, the formula for the bn's, because this is an even function times an odd function, the result of even times odd is odd, and you're integrating over a symmetric interval, so those coefficients all disappear. All the sign coefficients disappear. So this is the what we call the Fourier cosine series representation of the function x on the interval from, well, I could technically we computed it on the interval from -1 to 1, but for this problem I really only cared about what that representation looks like on 0 to 1. So that would be the even extension answer for this problem. And to get the Fourier series, I just go ahead and list out the full Fourier series here. And then n, capital N, is the total number of terms of the Fourier series I compute. Because technically, even though our answer is infinity, we can't put in an infinite number of terms. So we're only ever going to get approximations to the function x. And those approximations should get better, and we'll talk about that they do get better. But those approximations should get better as we use more terms. Here are the first 5 terms of this Fourier series. So this is the full answer. This is the Fourier cosine series answer for the representation of x. This is the first 5 terms. And you can see here, all I've done is taken, and this is the first period, this is the second period, across. I've extended +2, -2 in each direction, the even extension, and I've graphed a 2-term Fourier series. So just with 2 terms, it looks like this. If we wanted to see more terms, this is the code to do that. I've created a plot name, if you will, and that plot name is varied based on how many terms of the series we have. So if you want 20 terms, I can go up to 20 terms by plotting this Fourier series that I calculated here for capital N up to, say, 20, like I did here. So here's what it would look like. This is the Fourier series first attempt at representing this sort of seesaw graph. And as we up the number of terms used, you see how it gets better and better and better and becomes very accurate. I'm just looking at the interval from 0 to 1, becomes very accurate against the function x. There's still a little bit of rounding at the corners, which can't be helped, but this looks very good on the interval from 0 to 1. Now, similarly, if we go over to the odd periodic extension, it's what you would expect, f of x, negative f of negative x. I didn't have to define 0 here because the two match up at 0. I've got my Fourier cosine coefficients with the odd extension, f0, fo of x. Notice those disappear. Once again, the reasoning for that, an odd function, which the odd extension is definitely an odd function, an odd function times an even function is odd. So odd times even is odd. And because of that, we're integrating on a symmetric interval, so those coefficients go away. So it's actually the Fourier sine coefficients that survive. And here's what that looks like. And I should take that output and let's see, I think it's over here. Yeah. Take that output and where is it? Simplify assuming integer. So if you simplify this, assuming it's an integer, you'll get this, which means if we do the odd extension representation of x, then x is equal to, there are no a coefficients, so a naught is 0, so I don't get this constant term. So this is just the sum. N goes from 1 to infinity. The bn coefficients are there. Times sine n pi x. So this is what's called, because the cosine terms disappeared, this is what's called the Fourier sine series representation of the function x on the interval from -1 to 1, but technically I just care about it on the interval from 0 to 1 here. Okay, take a look at what this one looks like. So here is the first 5 terms, just like we did above. Here is the attempt at representing. So this is just with 2 terms. Notice with 2 terms on the Fourier cosine, we were actually pretty close. With 2 terms on the Fourier sine series, we are not close at all. And then here you can see that I do a sequence plot once again, and I'm getting sort of closer. For some reason, it was messing up the order on these. I'll have to figure out why that is. But you can kind of see here is once we get closer to 20 terms. It's doing a pretty okay job, so in the interval from 0 to 1. But here there's a discontinuity, right? So you can see the original function, there's a jump down to the next interval here. And Fourier series really have difficulty with these jumps. You can see here how it's trying to compensate by overshooting the jump and then bringing it back down. Here is a different way of looking at these from start to finish. You can just do a sequence of plots and then show for the first 20 terms how it gets better and better and better. But no matter how far out term-wise you go, you're always going to have, just like you did on this one, you're always going to have this little overshoot. It's something called Gibbs phenomenon. Notice that it overshoots the value 1 at the jump discontinuity. We'll talk about that a little bit later in this unit. All right, finally, we have the shift periodic extension. Now, the shift periodic extension is interesting here. I've gone ahead and put it in here for you to see. It's interesting because this function is neither even nor odd, which means we're not going to get any of the coefficients disappearing on us like we did previously. Let me double check. It looks like that disappeared, but I don't think it should have. Oh, well, they didn't completely disappear because the A naught term was still there. Okay, so even though a lot of these did disappear, the A naught term still survives. So we didn't get a complete disappearance here. Okay. But the sine terms are still very much there. Let me simplify the sine terms. Okay, and then we have the full completed series. So there are the first 5 terms of the Fourier series here. It's not the first 5 terms. It's up through the 5th orthogonal one, right? So sine of 1 pi x, sine of 3 pi x, sine of 5 pi x, they all disappeared here because sometimes this coefficient is 0. You can see that if n is, what would be... Yeah, if n is 1, 3, 5, 7, and so on, those all disappear. So what you end up with is this shift extension that you can see here. And on the interval from 0 to 1, here's the function x, and it's trying to sort of wrap itself around the function And it definitely gets better over time. You can see over time it goes from this to that, and then it gets better, but it still suffers from the same problem that the odd extension suffered from, namely that there is a jump discontinuity at 1. And out of all of the examples that we looked at here for this function, the only one that didn't have a jump discontinuity was this original one, because when you take and evenly extend this and then periodically extend it, notice there are no gaps formed in the periodic extension here. And that turns out to be a major deal when it comes to modeling with the Fourier series. The even extension is by far the best one to use here. So let me just finish out here by writing down what the shift extension ended up being. The shift extension for the function x turned out to be, remember a naught was 1, so you get 1 over 2 plus the sum. N goes from 1 to infinity, and it was only the Bn terms that survived there. So the Bn terms right here is the coefficients. So minus 1 n over n pi sine n pi x. And what we noted is really it's only the even values of n that contribute here. So this is actually a full Fourier series. It required both cosine and sine to represent this function because the starting function was neither even nor odd. When you do the shift extension, this is neither an even nor an odd function, so it technically required the cosine term there and some sine terms. So this is the full Fourier series representation of the function x on the interval from minus 1 to 1 via a shift extension. All right, so what have we learned from all of this? There are several lessons that I want you to take away from this. The first is Fourier series representations are always made simpler when your function is either even or odd. An even function times an odd function is odd, so one of the two coefficients will be 0 in this case. So if you're using the even extension or the odd extension, you'll never get the full Fourier series because the even extension makes the function even, so you'll only ever get the Fourier cosine series, and the odd extension makes the function odd, so you'll only ever get the Fourier sine series. So if a function is even, then its Fourier series reduces to the Fourier cosine series. And the Fourier cosine series is shown here below. And this is where an is 1 over L integral minus L to L of f of x cosine pi x. And if the function is an odd function, then its Fourier series reduces to the Fourier sine series. And the Fourier sine series is given by this function where its coefficients these are the only ones to survive. And finally, if you have the shift extension, then you're always going to end up with a full Fourier series. The periodic extension does not specify the endpoints. So notice I'm not including L or minus L in these extensions. You don't have to specify the endpoints. But we usually will be very wary of when there are discontinuities at the endpoints because of convergence. That's something that's coming up later. What we would love to have happen is the one-sided limits at L from the left and L from the right agree. That's what happened with the even extension on the example we just looked at. Everything connected up and the periodic extension just worked wonderfully. That's the best possible thing that can happen in terms of good convergence of our Fourier series. But that doesn't always have to happen. All right, so I want to turn around and redo everything we just did, except I want to do it with the function x squared. And I would like to write down all of the answers ahead of time. Let's see if you've been paying attention. And we're going to do this for L equal to 2. And then I'm going to go in and change the maple file to update it and see if we get what we thought we'd get. So even extension, x squared, well, that makes a ton of sense because x squared is already an even function. So this one will probably be the best once again. But we're going to say x squared is equal to, this is going to be a naught over 2 plus the sum, n goes from 1 to infinity, a n cosine n pi x over 2. And we're not even going to worry about the sign because we know the even extension isn't going to involve any of the sign terms. And this is where the a naughts are going to be 1 over 2 integral minus 2 to 2 of the even extension times cosine n pi x over 2 dx. All right, so that's the formula that we should be using in Maple here in just a little bit. All right, odd extension. What's the odd extension going to look like? Well, it'll represent x squared. There will not be any a terms, so there will not be any cosine terms. So we'll just be dealing with sine. And we know, so these are for all a-n's. And we know that the b-n's will be similar, 1 over 2 integral minus 2 to 2 of the odd extension times sine n pi x over 2 dx. Okay, shift extension will involve both cosine and sine, so we have a full Fourier series here. So it would be 1 over 2 integral minus 2 to 2, the shift extension function times cosine. And the shift extension function times sine. And we can come back and fill in these coefficients here in just a second. Okay, so let's take a look at it in Maple. All right, hopefully y'all can see that. We'll start with the even extension. So I'm just going to show you the changes you would make because probably what you're going to want to do on the homework is get one example completely done and then copy and paste your code to the next example and just change out the functions. So here we're looking at an interval of length 2 and we're looking at the function x squared. So I don't have to change my even extension. Let's plot these just to make sure everything's looking right. So there's the even extension. Looks good. Looks a lot like the function x squared, like it's supposed to. Let's calculate the coefficients. So there are the coefficients for an. Unfortunately, I've got to right-click on that again. So we're going to simplify it, assuming it's an integer. So there are our coefficients for the a-n's. So we know that this is 16 negative 1 to the n over pi squared n squared. And in particular, a0 is 8/3. So you're going to end up having 8/3 is going to be what? 8/3 divided by 2, right? So you're going to end up having 8/6, which is 4/3. Plus the sum, n goes from 1 to infinity. Like this for the Fourier series. So that's the Fourier series representation of the function x squared on the interval from -2 to 2. You can see that the coefficients for the bn's are 0 once again, as suspected. Here are the first 5 terms of the Fourier cosine series. Here you've got to be careful. I shifted this forward and backward by 2, but since we're on the interval from -2 to 2, the length of the interval is 4, so you'll want to shift your graph of the even extension back and forth by 4. So here you have, and I probably want to show it even more here. Let's see. Since it's length 4 times 3 would be 12. So I want to go all the way up to 12 on each side. No, that would be 24. I want to go up to 6 on each side. So there are 3 periods of the even extension, and it looks a lot like the previous one. You know, this is our attempt at sort of representing that, and then over time that attempt does get better. Right? This looks an awful lot like x squared now. So our attempts are getting better, and not bad. All right, how about the odd periodic extension? Okay, we're going to change it over to a length 2 interval, function x squared, and I don't need to change the rest. So this almost looks correct. Interval from -2 to 2. All right, so there is our odd extension for the function x squared. Notice if I periodically extend this, we're still going to have the jump discontinuity issue because the limit from the right here doesn't match the limit from the left here. So coefficients, they still disappear. How about the bn's? Well, they're slightly different. And if I simplify this, we get something that looks quite a bit more difficult than the ANs did. So this ends up being -8 n squared pi squared, -1 to the n, plus 16, -1 to the n minus 16, all over n cubed pi cubed. So those are the coefficients for the bn's that would go right here in the Fourier sine representation of this function. All right, keep it going. So here are the first 5 terms. Notice once again we had some terms disappear. We've got pi halves pi. Actually, no, I think we got them all. No, none of the terms disappeared on this one. Once again, I'm going to change it over to 4 and -4 because the length of the interval is 2. So, you know, I go -2 to 2, which has length 4, so I can copy that 4 units in either direction. And we'll go -6 to 6 just to see it all. And so there is our first attempt at the representation of the function, the odd extension of the function x squared. We'll do a couple of more looks at it, and there is the Fourier series representation of that. But notice we still get those large overshoots. And as time goes on, can we make this better? So with 20 terms, we still have a ton of jaggedness. You see how it's getting better. Let me see if I can up this a little bit. Let's go to 40. The more terms you do, obviously, the higher cost you pay in terms of computing it. But Fourier series are pretty easy to compute. So there's our best view, maybe, right in there. It didn't display them in sequence, so it's hard to see. But there you're starting to get a really good representation of the function. And of course, if we went to infinity, then theoretically there would be no error on the interval from -2 to 2. Except, unfortunately, there's always going to be a little bit of error at these endpoints. And like I said, we'll talk about that later. Okay, finally, on the shift extension, we've got 2 different sets of coefficients we need to look at here. So in the shift extension, L is 2. We're looking at the function x squared. And I don't think I need to change the rest of that. So let's make sure it looks right. Interval -2 to 2. So there's the shift extension. You just take x squared and move it over. Okay, computing its cosine coefficients. So the cosine coefficients here are given by those, and a naught is 8/3 once again. That's not surprising that it's 8/3 because the Fourier cosine value for that was 8/3. This value is the average value of the function x squared on the interval from 0 to 2. So 8/3 out in front, so a naught turns out to be 8/3, and all of the rest of the coefficients for cosine terms turn out to be this. Now let's look at the sine terms. Sine terms are pretty simple. And compute the first 5 terms of the Fourier series. It's decidedly more complicated because it involves both sine and cosine. This is the full Fourier series. We're going to go plus and minus 4 here on the interval from -6 to 6. All right, so what you can see here is we have a shift extension here. We've got the original shift, and then we've got 2 copies to either side. So computing the plot, you can see here what happens as we go. We get better and better. That's probably the best that we can do at this point. With 20 terms, there's still a lot of jaggedness. There's still the overshoot at the jump discontinuity here, where you go from 0 to 2, then you jump to go from 2 to 4. That jump is causing a lot of issues. We'll talk about why later. But that's the shift extension. So this has been a pretty simple lecture, I hope. Maple is going to do a lot of the heavy lifting. You just need to know the formulas, and you need to understand when you'll get only the cosine series, when you'll get only the sine series, when you'll need the full Fourier series, and the freedom that we have in terms of choosing those extensions to hopefully get the one with the best error. And that's what we're going to be focusing on coming up on Friday, are some of the error formulas for these topics. I encourage you to take a look at the Fourier series document that I placed up, plotting Fourier series in Maple. There is another one called Fourier series examples. I encourage you to look at that one as well. That one has a little bit of information about convergence formulas that we didn't go over here, but we will go over Fourier convergence theorem and things like that on Friday. All right, y'all have a wonderful day, and I'll see you back here on Friday. Thanks.